Okay, so today we're talking about the geometry of molecules. And so when we determine the shape of a molecule, first thing that we have to know is how many valence electrons does that atom have, or do the atoms that make up that molecule, because that's what a molecule is. It's a group of atoms that are bonded together. So valence electrons, we have to know how many each of the atoms has. So as a review, valence electrons, we have oxygen here. Oxygen has an atomic number of 8, and so 2 of those electrons are going to go in the first shell. If oxygen has 8 valence electrons, or I'm sorry, has 8 electrons, then 2 of them go in the first shell. That leaves 6 electrons left over, and so we see here we have 6 electrons on the outer shell, and those are the valence electrons. So oxygen has 1, 2, 3, 4, 5, 6 valence electrons. Now, when we look at the periodic table, we can figure out how many valence electrons each of the elements has very easily. And to do that, all we have to do is we look at the group numbers. So we have here group 1, 2, 13, 14, 15, all the way up to 18. Those are the ones that we can easily figure out how many valence electrons they have, just based on the group that they're in. So here with group 1, that has 1 valence electron. Group 2 has 2 valence electrons, and you'll see the trend here. As we jump across the transitional metals to group number 13, that one has 3 valence electrons, group 14 has 4, group 15 has 5, group 16 has 6, group 17 has 7, and lastly, our noble gases have 8. So group 18 has 8 valence electrons. So anytime we're trying to figure out how many valence electrons does this element have, we just look at the periodic table and figure out what group is it in. We can figure it out very easily. All right, so let's start looking at the valence electrons, how we represent those valence electrons in Lewis dot diagrams. So here with oxygen, we have oxygen in the middle with the atomic symbol, and then oxygen, of course, has 6 valence electrons. We know that. And so we place those around the atomic symbol in an order where we have pairs on each side. So oxygen has 6, so we place 1, 2, 3, 4, and then we come back and we pair up electrons. 5, and then 6. So oxygen has 6 valence electrons. Now, as we're forming covalent bonds, those elements, those atoms are going to bond together. And so what a covalent bond is 2 atoms that are sharing electrons. So here we have oxygen. Again, oxygen has 6 valence electrons. We saw that earlier. So we have the 1, 2, 3, 4. We have 1, 2, 3, 4, and then we had 5 and 6 there. Now hydrogen has 1 valence electron, and so hydrogen is a special case because it only needs 2 electrons to have a full outer shell. And so hydrogen, that 1 valence electron, it's going to share that electron with oxygen, and oxygen is going to share 1 electron with hydrogen. And so here, this completes a pair. We have another hydrogen atom there that also does the same thing. It's sharing electrons, so it forms a covalent bond. And so here we have 1 oxygen and 2 hydrogen atoms forming H2O, or a water molecule, using covalent bonds. Now, when we're using, or when we're drawing Lewis dot diagrams for specific molecules, what we're going to do is we're going to start off by first counting up the number of total valence electrons in that molecule. Now, for ions, we'll subtract or add an electron based on the charge of the ion, but don't worry about that right now. So here we have a molecule. We have 1 phosphorus and 3 fluorine atoms. This little subscript here, the 3 down there, tells us that there are 3 fluorine atoms. If the 3 was moved over, it would mean that there are 3 phosphorus atoms. But here, PF3 tells us there's 1 phosphorus and 3 fluorine atoms. Now, if we count up, looking at the periodic table, how many valence electrons total we have, phosphorus has 5 valence electrons, fluorine has 7 valence electrons. So we have 1 phosphorus and 3, so we have 5 phosphorus valence electrons from phosphorus, and then we have 7 valence electrons from fluorine. So we have 3 fluorine, 1 phosphorus, so it's 5 plus 7 plus 7 plus 7 gives us a total of 23 electrons. We divide that in half to figure out how many pairs of electrons, because electrons pair in groups of 3. So here, with PF3, we have a total of 26 electrons, 26 valence electrons, which makes up 13 pairs of electrons. So we're going to organize those pairs of electrons around the Lewis dot diagram for the molecule. So here, when we create these covalent bonds, when we create these molecules, we want to follow what's called the octet rule. The octet rule tells us that there are 4 pairs of electrons that go around most atoms. All right? I say most because there are some times where you'll have an atom that will have more than 4 pairs, but most of them will only have 4. So 4 pairs of 2, which gives us 8 total of electrons to fill that outer shell. Hydrogen is an example of one that doesn't take 8. Hydrogen can only have 2 electrons that fill the outer shell. So hydrogen will have 2. Most atoms will need 8. So here we have oxygen. We have 4 pairs, gives us a total of 8 electrons. All right, so as we're creating the molecules, with PF3, remember we have 13 pairs of electrons that we have to organize around the molecule. So we're going to take PF3 and we're going to figure out which one of those elements is by itself. Of course, there are 3 fluorine, so the P is going to be our central element, our central atom. And then we're going to organize the fluorine around the phosphorus. So here we have phosphorus as the central element, central atom, and we put each of the 3 fluorines around the sides of the phosphorus. Once we have that, we can start to place our groups of, or our pairs of electrons. Remember, we have 13 here, so we're going to start off, I'm going to start putting electrons around the fluorine. And so here we have 1 pair, 2 pairs, 3, 4, 5, 6, 7, 8, and 9. So now we have 4 pairs of electrons left over, because remember, PF3 has 13 electron pairs. So now I'm going to indicate the shared pairs of electrons. The way I'm going to do that is I'm going to use a straight line to show that these 2 elements, those 2 atoms, are sharing a pair of electrons. So here we have 1 shared pair that gives us 10 pairs. We have 1 there, that's 11. We have 12. And so we still have 1 set of paired electrons that's left over. And so we're going to place that shared, or I'm sorry, we have 1 leftover pair of electrons. We're going to place that pair with the central atom up here. All right, so now I've placed all 13 of my electron pairs. Now, there's some atoms that are able to form more than, or they're able to share more than one pair of electrons at a time. Carbon and oxygen are an example of those. We see here carbon, nitrogen, oxygen, phosphorus, sulfur, and sometimes chlorine. They're able to form triple bonds, double bonds, things like that. They're able to share more than one pair of electrons. So an example of that is carbon and oxygen. When we add this up, carbon and oxygen will have 5 pairs of electrons. So 5 pairs of electrons. We place one over here with carbon. That leaves 4 pairs. Place one over here with oxygen. That leaves 3 pairs. Both of these atoms still want to form that, or want to comply with that octet rule. So we have one set of electrons here, one set here. They both need 3 more sets of electrons. And so we fill in with a triple bond between the carbon and the oxygen. All right, so these elements here, carbon, nitrogen, oxygen, phosphorus, sulfur, can form multiple bonds. They can share multiple sets of electrons. Okay, so here we have SF4, sulfur, and fluorine, but here we have 4 fluorine instead of 3 like we did with phosphorus. Sulfur has 6 valence electrons, fluorine has 7. So when we add those up, we have a total of 34 electrons, which gives us 17 pairs. So we go through the process again. Sulfur is going to be the central element, the central atom. We place the 4 fluorine atoms around the sulfur. All right, I place them like this on purpose. Now we start adding the pairs of electrons. We have 17 to go. So we place 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we still have 5 pairs of electrons to place because we only have 12 around the fluorine. So we start adding in the shared electrons between sulfur and fluorine. So there's 1, 2, 3, and 4. But we still have 1 pair of electrons that are left over. So if everything has the octet rule that has been fulfilled, and we still have leftover electrons, we're going to place those around the central atom. So we have 1 pair of electrons that's left over. That's going to go up here above the sulfur. All right, so here's an example where sulfur has more than just 4 pairs of electrons. Okay, so that's how the elements fit together. As they fit together, they'll form specific shapes. All right? The main shapes, the main geometries that you need to know are these here. We have linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Each of these will have a very specific shape. So let's start off with linear. Linear, I like to describe as it's a straight line, and the atoms will line up like you're holding 2 balloons together. All right, so you may have a central atom, and then you'll have two atoms, one on each side. The next one, trigonal planar. This would be like holding 3 balloons together. They're evenly spaced out on a plane. That's why it's trigonal planar. So this here is a diagram that shows that setup. The next one, The tetrahedral is like holding 4 balloons together. We can see that here in this picture, and then this here shows us what it looks like. That's the diagram that represents a tetrahedral geometry. Now these here, like this this open triangle, the triangle that's not filled in, that represents an atom that is coming toward us away from the central atom. So it's arranged close to us, between us and the central atom. The triangle with the lines, that represents an atom that is placed behind the central atom. So this represents a 3D diagram. All right. The next geometry is the trigonal bipyramidal. This one is like holding 5 balloons together. You can see here in the picture, we have the 4 back here and then 1 up front. We can see the diagram here. Now, since there are 5 balloons with a central atom inside, these geometries do not follow the octet rule. This will be one of the shapes where you'll have more than 4 pairs of electrons that surround that central atom. And same thing with octahedral. Octahedral is like holding 6 balloons together. You have that central atom, and then you have 6 either atoms or pairs of electrons that surround that central atom. All right, so let's look at how do we figure out, once we know the Lewis dot structure of the atom, or the molecule rather, how do we figure out which of the shapes it's going to be? We have this nifty little chart here that shows us all the different shapes, all the different configurations that we'll have with the molecules. So first thing that we do, we draw our Lewis dot structure, which starts off by counting the number of shared electron pairs. All right, we count up the number of electron pairs, and we create our dot diagram. Once we have the dot structure, we count how many of those electrons are shared. How many of them have 2 atoms that are sharing that pair of electrons. Then we count up how many electrons are unshared. How many are just around that central atom. Once we add those together, if we add them together, the shared electrons plus the unshared, and it comes up with 2, then we know we have a linear geometry. If it comes up to 3, it's trigonal planar. If we add those up, for 4, it's tetrahedral, 5 is trigonal bipyramidal, and 6 is octahedral. Now, once we know the basic shape, then we're going to look at the number of unshared electron pairs, and it'll tell us the type of structure for that geometry. And we'll use an example to show you exactly what I mean. So here, we're going to go back to the example of PF3. And to remind you, PF3, subscript tells us there are 3 fluorine. With phosphorus, there are 5 valence electrons. Fluorine, there are 7 valence electrons. So we add up the number of valence electrons total, 26 electrons, gives us 13 pairs. We place phosphorus, since phosphorus is the lone atom, it's by itself, there are no other phosphorus. We're going to place phosphorus in the middle and then arrange the fluorine around it. We have 13 pairs of electrons, so let's place those first. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have our shared electron pairs, 10, 11, 12. And then we have 1 unshared, gives us 13. All right, so when we're looking at the geometry, these electrons around the fluorine, we're not worried about those ones. all that we want to know are the electron pairs around the central atom. So, here I've taken away those electron pairs around the fluorine, and all we have are the pairs of electrons that are around the phosphorus. So, with the phosphorus, we have 4 pairs of electrons. So, right here, 4 pairs of electrons. That tells us it's going to be tetrahedral. We know it's going to be one of these tetrahedral geometries. Now we look at the shared electrons. We have 3. 1, 2, 3. So that leaves 1 pair of unshared electrons. That's right here. So, tetrahedral shape. We have 1 pair of unshared electrons. So we're going to look at where do those two meet. So if we go over from the tetrahedral shape, we have 1 pair of unshared electrons. We come down from there. And it tells us the shape of this molecule is trigonal pyramid. All right. If you have any questions, if there's anything that we just went over that you do not understand, always remember, ask questions, ask me for clarification, and that's what I'm here for. All right? Whatever you need, let me know.